Hello, everyone, and welcome to this talk. My name is Alan Glazner, and I'm a professor emeritus of geology at the University of North Carolina at Chapel Hill. And this is a recording of a talk that I gave in November at for the White Mountain Research Center in Bishop, California. That was a virtual talk. This is a virtual talk. Then, as now, I'm going to pretend we're in Bishop, and I'll talk about the mountains outside, even though you may be far from Bishop. And my main thrust of the talk is going to be the changing plate tectonics of Western North America and what that means for earthquakes and the eventual geologic evolution of this part of the world. So let's jump right in and look at this amazing satellite photo taken by an astronaut on the International Space Station. It's looking west across Owens Valley. I've highlighted the towns of Lone Pine, Bishop, and Mammoth Lakes up here. Here are the White Mountains, the snow-covered Sierra Nevada. And you could run many college courses on geology just looking at this photo alone. There is so much to see here, but what I'm going to focus on is the plate tectonic setting, the Ridgecrest 2019 earthquakes, and what that all means for the eventual evolution of California. But before we get into that, I would like to mention that our new book, Geology Underfoot in Death Valley in Eastern California, which is a rewrite of the book that Bob Sharp and I wrote in 1997. And on this one, Art Sylvester collaborated with me, and we've done a major rewrite and many additions to the old book, and it's all in color. So it's at the printer right now, and if we're lucky, it will be out in January. A lot of the stuff that I'm going to talk about tonight is covered in this book. And so if you are interested in this talk, you might be interested in this book as well. So let's get started by looking at the photo that I showed earlier, but the entire photo, not just the crop part I showed. So we're looking at west again, from central Nevada across the White-Inyo Range, Owens Valley, Sierra Nevada, Sierra foothills, Central Valley, to the coast ranges. Here's Monterey Bay and the San Luis Obispo area, and then the Pacific Ocean behind. And you might notice some gashes in the landscape, like this one here, and that's the San Andreas Fault. And in the big picture, if you step back and look at the plate tectonics of North America, then everything west of the San Andreas Fault, including this coastal part of California, is part of the Pacific plate, and everything east of it, shaded in brown here, including the Sierra Nevada and Owens Valley, is part of the North American plate. But it turns out that it's way more complicated than that. And the focus of this talk is going to be that it looks like a new plate boundary is forming, and that this part of most of California is being captured and sliding to the north, which is to the right or in this direction, along with the Pacific plate. And a new plate boundary is forming more or less where Owens Valley is now. The rearrangement of the plates is caused by a misfit at the plate boundary down in Southern California, where the San Andreas Fault makes a big bend. So we'll talk about that. And the Ridgecrest earthquakes, the Owens Valley earthquake of 2000, or the Owens Lake earthquake of 2020, and the great 1872 earthquake in Lone Pine were all parts of this process. It's a multi-million year process. It's not going to happen in our lifetimes by any means, but it is an ongoing thing, and understanding it is really helpful to understanding the geology of this part of the world. I'm going to draw on many, many sources during this talk. Some of this is my work and the work I've done with my close colleagues, John Bartley and Drew Coleman, over the years, and of course, many, many of our own students. Some of it is drawn from the work that Art Sylvester and I did working on the Geology Underfoot book. And an awful lot of data and figures are going to come from the US Geological Survey, the IRIS Seismic Consortium, and the UNAVCO GPS Consortium. There are just amazing data sets out there that you can play with, and I'll show you some of that in this talk. So let's look at the classic plate tectonic view of Western North America. We've got the North American plate, which stretches from the San Andreas Fault all the way across North America and out to the middle of the Atlantic Ocean, south of Iceland. And everything west of the San Andreas, including the entire Pacific Ocean, basically is the huge Pacific plate. And those two are sliding against one another in California along the San Andreas Fault. It's fairly simple up here in central and northern California, where the Pacific plate is moving in the direction of this arrow relative to North American plate moving in the direction of this arrow. We call that a right lateral fault because if you're standing on either side of it, the other side is moving to the right in a horizontal sense. That's very important, and we'll be using that term a lot during this talk. There's another major fault in California called the Garlock Fault that gets much less press. It's a major left lateral fault. And the Ridgecrest earthquakes occurred in this area and kind of mimic the San Andreas and Garlock faults in miniature, as I will show you. The San Andreas is quite complicated in Southern California because it comes out of the Gulf of California and then makes a big bend in the Los Angeles area before it resumes this trend parallel to the motion of the Pacific plate. So here, this Baja Peninsula and Southern California are basically ramming into the Mojave Desert and thrusting up the transverse ranges. I grew up at the base of the transverse ranges. There are 12,000 foot peaks there, pretty close to the ocean. And they are there because of this big bend. So that's the misfit that I was talking about. And we will come back to that. Down in the Gulf of California, a new ocean basin is forming. These heavy dark red things are spreading centers where new oceanic crust is being born as basalt is erupted to form new ocean floor. That has rifted Baja away from the rest of Mexico, but that stops down around the international border and turns into just sliding between these two plates. And then things are complicated up in the Pacific Northwest, and we will skip that for tonight's talk. This arrangement of the San Andreas Fault trending northwest and having right lateral slip, and the Garlock Fault trending northeast and having left lateral slip is consistent. This was recognized long ago. It's consistent with this whole area being squeezed in a north-south direction. If you built a clay block like this and put some cuts in it and squeezed it north-south, you would get motion on those cuts in the direction shown by the pink arrow. So that's kind of the overall stress state of this part of the world. And as I mentioned, the Ridgecrest earthquakes mimic that quite well. So the Ridgecrest earthquakes took place on July 4th and 5th, 2019. On some of the slides, you'll see July 6th because the official times of earthquakes are in universal coordinated time, which is basically like old Greenwich Mean Time. And so it was 3:30 in the morning in England when that earthquake, when the big earthquake happened. It was 8:30 at night on July 5th in Ridgecrest. So don't let that confusion mess you up. Two big earthquakes. The first one was a magnitude 6.4. The second was a magnitude 7.1. And I was originally scheduled to give this talk in March of 2020, and we canceled it for good reason back then. So the 2019 earthquakes were a lot more immediate at that time, but I'm going to show you some video and so forth to kind of take us back and remember what it was like back in 2019 when these earthquakes happened.
Even in Los Angeles, more than 150 miles away,
it continues.
This is a very strong earthquake.
Pretty strong here.
8:21 here on the air. We're experiencing very strong shaking. Wow. I think we need to get under the desk.
All right, we're going to go to break. We'll be right back.
We'll be right back.
Wow.
The magnitude 7.1 quake came just one day after Thursday's 6.4 jolt, which at the time was the largest earthquake to hit California in 2 decades. That quake turning life into chaos without warning turned out to be a foreshock, but this is what's left behind. The region was just starting to clean up. Elsewhere in Ridgecrest, security video captured the shaking at a laundromat and inside this convenience store. The tape stops as the power cuts out. We talked to the store owner, Tony Abdulatif. How much do you think you lost here?
Be honest with you, from yesterday and today, I would say about 100,000.
No insurance.
No insurance for the earthquake, of course.
Okay, well, you might want to secure that flat screen TV to the wall if you live in earthquake country like this. So what I'd like to do is give you a little primer on earthquake waves and why earthquakes feel the way they do, earthquakes of different size, different distances from you, and just how that all shakes out, so to speak. So let's talk about the different kinds of waves. There are three main kinds of seismic waves. One type, the fastest type, is called P waves, and they move, as this diagram shows, as compressional waves, going like this, just like sound moves through air. So you're basically hearing my voice by these kinds of waves being generated by a speaker, pushing the air this way and then moving your eardrum, and that's interpreted in your brain as sound. P waves are the fastest in the crest. They go around 6 kilometers per second or 4 miles per second, but they are pretty high frequency and they peter out pretty quickly with distance. Another kind of seismic wave is called S waves, and S is often, you remember that as shake waves, and they're by shaking back and forth or up and down or some combination of all of those things. S waves are slower than P waves. They're also lower frequency, and they also last longer than P waves. They don't die out as quickly. P waves and S waves are both called body waves because they can travel in the interior of the earth. The third kind of wave, and there are several subsets of this, are called surface waves. And they are by far the slowest waves. They're the longest wavelength. They're much slower in speed and also in shaking frequency. But they also are the most persistent. These waves can go around the world and be detected as they come back the second time. So this is kind of a complicated slide. We've got shaking going on 3 different things here. And remember, the S waves can shake in all different directions as well. And an earthquake generates all of these things. So all of these waves take off when the earthquake happens, when the rocks slip on either side of the fault. And then they go into or along the surface of the earth, and all kinds of crazy things can happen here. So this is just a simple diagram showing an earthquake generating waves that take various paths and showing some of the things that can happen. So here's an earthquake and it generates a P wave, and they take curving paths through the earth. And this one comes up and bounces off the surface and generates a P and an S wave reflection. And the P wave comes over and ends up coming out here. And the S wave ends up coming out over here. And those can generate P and S waves that come out on the other side of the world. And waves can, here's an S wave that comes down and hits the core and splits into a P and S wave that come back to the surface. And here are waves that go through the core and all. And this is how we know what's inside the earth. Seismologists decode these waves. But this is just a small fraction of the number of ray paths that waves can take. So seismograms are really complicated. But I'd like to show you some seismograms for the magnitude 7.1 earthquake in Ridgecrest, just so you can get a feel for this. So the earthquake was here. Here's Ridgecrest, the focus of the earthquake. Bishop is up here, and the nearest quality seismometer that I could find was at Tenemaha Reservoir, which is maybe 20 miles or so south of Bishop. And then I chose some other ones just out of the amazing IRIS data set. Anybody can go there and look up the data like I've done here. So I picked one from Albuquerque, one in Texas, one in Massachusetts, and one in Peru. So let's look at what those seismograms look like. So here they are. All of these stations are lined up at 3:30 a.m. Universal Time, or 8:30 p.m. July 5th in Ridgecrest. And they all cover, what do they cover? 50, 30, about a little over 20 minutes of time. So Tenemaha Reservoir, the P wave arrival is marked by this red line, and the S wave, which is kind of hard to pick out from the P wave, by this blue line. And I've blown that up down here, this part of the record. The P wave arrived 25 seconds after the earthquake. It took 25 seconds to travel that distance. And the S wave arrived 43 seconds after the earthquake. And that 18-second difference is a measure of how far away the earthquake is. And you'll see that that increases as we go to farther and farther stations. The P wave hits. If you were sitting in Bishop, you would have felt the P wave as a jolt, but P waves are high enough frequency. They vibrate so fast that they don't shake the building like this. They vibrate too fast for that. So you'd feel that jolt and know something was going on. And then in this case, 18 seconds later, the S wave hit. And you can see a lower frequency here with these higher frequency P wave jiggles superimposed on it. But S waves tend to make buildings shake kind of like this. So that you really notice. And I've been in earthquakes where you feel the building kind of go boom, and you go, what was that? And you wait around a little bit, and then suddenly the building goes like this. That's just what happens. If we go to the Albuquerque record, you'll notice that the P wave arrival is much weaker. There's much lower amplitude here, not a whole lot of shaking going on here until you get to the S waves, and then they are significantly bigger. And then we're seeing surface waves out here. The reason that these lines are split into two is that the red is the initial P wave arrival coming in, and the orange is a bounced P wave that comes in right after it. And the same thing for S. So these are the ones that are generated, curve back up to the surface and bounce off and come back in. If we go to Texas, again, not much in the way of P waves. They're dying out. The S waves are dying out as well by the time you get that far away, and you're mostly getting surface waves. Massachusetts, almost nothing in the P wave and the S waves, and then a big surface wave signal. And if we go all the way to Peru, now the vertical scale on this one is blown up quite a bit, by a factor of 100. So this would be much smaller if shown at the same scale as these, but for some reason there's P wave and S wave energy in there, and then you get these long period surface waves. This gap is 5 minutes, so some of these surface waves take about a minute to pass by. That's the time it takes the crest and the trough of these to go by. Now, this business of the P wave being kind of subdued relative to the S wave has led to a lot of people interpreting animal behavior as, my cat predicted that earthquake. So let's look at that here. This is a YouTube video from a cat adoption cafe near Osaka. It's just before 8 in the morning, and the cats are all sleeping, waiting for people to come in and pet them and maybe even adopt them. And the title on this is Cat Sense Earthquake Before It Happens. So let's run the video. Cats are sleeping, and then, oop, what was that? They just all woke up at the same time. A couple of them started moving around. What's going on here? This guy on top is really watching. And then the S wave comes in and starts shaking. So they woke up to that little P wave jolt, and then the S wave came in and really shook it. And the cat's living in the high rises up here thinking, I'm getting out of here. I don't like this high rise living. So that is a good example of that, of the high frequency, lower amplitude P wave coming in and sort of hitting the building, and you wake up, but it's really the S wave that gives you the good jolt. Now, there are just some amazing visualizations of earthquakes out there, and I want to take the time to show you one that is just incredible. I'm actually using the 2010 Sierra El Mayor Cucapá earthquake in northern Baja California, which was about the same size as the Ridgecrest earthquake. But at the time that one happened, an array of seismometers was in place in the center of the US. This array moved across the US, recording data to understand the structure underneath North America. And so the people at IRIS, there's the URL for it right there, made these incredible animations. What you're going to see is when a station lights up red, it's moving up, and when the station's blue, it's moving down. So let's start the video. There's the earthquake, and you can see the waves propagating outwards. That's so good. Let's do that again. So the first thing you're going to see is the weak P wave and the S waves. These are the S waves coming by, and then the higher intensity ones are the surface waves here. And you notice they're curved in an arc. They were going out radially away from the earthquake. So there was a bunch heading west and southwest into the Pacific, just as these are heading east and northeast across the US. And if we let it run, those surface waves pass by, and the stations kind of jiggle for a while there, and they waves pass through the eastern US. And then interesting things happen. So I'm going to go forward, and now I'm not showing you actual data, but I'm showing you a simulation of those waves done by people at Princeton University. And I'm going to stop and speed this up. So the waves that peter out like the S waves are already petered out here. These are the main surface waves here, the same red blue thing. And they spread outward. And if I pick this up after about 15 minutes, they've hit the East Coast. And by about 40 minutes, they've hit Western Africa. And if I keep going, they go all the way around the world and converge at the antipode. This is the place on the Earth opposite Ridgecrest, or Sierra Mayor, actually, Baja California. You notice this is at about 1 hour and 25 minutes after the earthquake happened. So if we go back to this animation and we see the waves moving across, now think about what you might predict at 2 times an hour 25 or 2 hours and 50 minutes after the earthquake. I'm going to speed it up to 2 hours and 40 minutes and then let it run. And incredibly, you see those surface waves come back in from the northeast. They've gone around the world. These are the ones that left to the southwest and went around the world and came back. And then these are the ones that went to the northeast, going around the world and coming back through the array. These are incredibly sensitive instruments, and it's just astonishing that they can detect these things having traveled around the world like that. So hats off to the seismologists. Okay, so let's talk about the earthquake itself. The first earthquake, a magnitude 6.4, was on a left lateral fault, and the bigger one, the July 5th magnitude 7.1, was on a right lateral fault. And most of the really awesome exposures of offset are within the China Lake Naval Air Weapons Center. So you have to have special clearance to get in there. So I haven't been in the base to see this, but there are lots and lots of beautiful photos. This is a helicopter shot by the USGS of a dirt road offset about 4 meters, 12, 13 feet by this right lateral fault. It's right lateral as clear as can be. It offsets that fault to the right laterally. Here's the fault cutting through a dry lake. There's some vertical subsidence here because the loose lake sediments kind of settled down. You get all sorts of weird local topography. This is looking northwest across the base there. There was tremendous building damage in Trona. Ridgecrest was remarkably unscathed. Newer buildings built to code. There were a lot of older buildings in Trona, and Trona was damaged quite heavily, even though it was farther away. If you want to go see some of this offset, Caltrans unfortunately fixed the road pretty quickly. This is a truck on Highway 178 heading east toward Trona and Cyril's Lake, and it was cut and offset a meter or so by the earthquake, and they fixed it, and you can't see any offset there now. But this fence on the south side of the China Lake Naval Air Weapons Center was offset at least several months ago, and I hope the Navy doesn't go in and fix it, because it's a great marker for this right lateral offset of about a meter along this trench here, which is the fault trace. So hopefully they'll leave that around and you can go see that. Something that you will probably be able to see for a long time is this feature here. This is in the Trona Pinnacles, not far from that last picture. Beautiful tufa mounds on the built within old Lake Cyrils during glacial times. And a lot of them kind of look like stone giants to me, this one in particular, and this one looks like somebody with a robe on, and there's their head. And this was in 2016. And if you go back there now, their head is down here in the foreground. This shook off during the 2019 earthquake and landed and made a big pit right here, and then you can see how it rolled out to here. It's about 5 feet tall, so it's a substantial rock. And when you see other loose rocks just laying around out here, you can bet that they fell off of these towers during previous big earthquakes. So I'm going to show you now is a USGS animation of the earthquakes and aftershocks. There are three main faults in this area. There's the Garlock fault, left lateral, that I talked about earlier. There's a right lateral fault, previously unnamed, even though it was mapped on geologic maps, at least in places, and then a completely unknown left lateral fault here. The first earthquake happened, interestingly, right at this intersection. And so here come the aftershocks, and I'm going to stop that right now because immediately seismologists notice something funny. Normally, aftershocks make a linear pattern on a map following the fault that generated them, but this one made a 90-degree bend. It's a kind of like a backwards L or a sideways V. And that was a hint that there was more than one fault involved, and that the one that slipped, and they could see it slip because it broke Highway 178 and so on, was this one. But there were clearly earthquakes happening on this one that they really didn't know about. So let's let that run, and it'll run through July 5th and into the evening of July 5th. And at 3:30 a.m., there comes the big magnitude 7.1. And then earthquakes started piling up from it. Now, these aftershock patterns are fascinating. First, the blue ones from the first earthquake make that 90-degree bend, which is very unusual. And the second interesting thing is that the aftershocks, the red aftershocks of the 7.1 earthquake, very intense in here, and they stop at the Garlock fault. They just stop. There's one little aftershock in the Mojave Desert, but the rest of them just stop there. And if you go to the northwest, they stop here. This is the Airport Lake area, and they stop right there. And then there are aftershocks around this area. This area right here had almost no aftershocks. And this is the geothermal area. And the idea, the likely explanation is that the faults down here, a lot of rock pressure on them, and they're locked, and stress builds up from plate tectonic motion of the Pacific plate against North America. But in the area of the geothermal production, there are a lot of fluids in the rock, hot fluids that lubricate the faults and probably prevent buildup of a lot of stress. And so it had a lot of stress down here, and it broke, and stress up here toward Highway 395 and Hayway Reservoir, but this area was left out of that. This is the China Lake Airfield and Naval Weapons Center, and there was estimated around $5 billion of damage to equipment at China Lake. The one thing on China Lake that survived with basically no damage at all was the geothermal installation, which was built to specs to withstand a magnitude 7 earthquake, and it did that. So that's a good thing. Here I've taken the earthquake catalog. I've taken about 111,000 earthquakes, magnitude 0 and greater. Magnitude 0 is not no earthquake. This is a logarithmic scale, so it's a very small earthquake, but it's still ground shaking. And I plotted them against time in July. So here's the magnitude 6.4, and then it's aftershocks, and they kind of tailed off, and then boom, the magnitude 7.1. These plotted symbols are scaled according to the amount of ground shaking they caused. And so most of the shaking happened in the two biggest earthquakes. And in fact, most of the shaking and the energy release happened in the big earthquake. You can see the numbers. There were 88,000 greater than a magnitude 0, 90 greater than magnitude 4, 2 greater than 6, and only 1 greater than 7. That's how earthquakes behave. So even though there were lots and lots of aftershocks, 100,000 or more that could be measured, most of these you would not feel, and they don't do anything. It's the big ones do all the damage. Now these seismograms kind of look like sound waves, and seismologists like to take them and speed them up and let you hear the sound that they would make. And so I found this on YouTube. This is an audio realization of the 7.1 earthquake, taking data from a seismometer not too far from the epicenter. And this is the seismogram. These are power spectra and so forth, which are more complicated. But the blue lines are aftershocks, and you can see the size is 3.6, 4.3, and so on. Brace yourselves. This is kind of loud and dissonant, but here's what it sounds like. Well, okay, that goes on and on, but it sounds a lot like hail hitting a metal roof or something. It's really kind of interesting to hear that. And that was sped up 100 times. So that what I showed you was about 40 minutes worth of real time compressed. So let's talk about what happened during those earthquakes when they slipped and what that might mean for the future. So here's the aftershock pattern. And remember the three faults: the Garlock fault, the right lateral fault, and the left lateral fault. So I've idealized them in this kind of modern art here on the right side of this panel. And if we look at what happened, so this is before any earthquake slip, and just schematically, if we look what happened after the magnitude 6.4 left lateral event on the 4th of July, that moved this block left laterally relative to this block and opened up a gap here. And basically this fault, but all these faults have pressure on them that keeps them locked until the stress builds up enough for them to break. And when this one slipped, it released pressure and basically unlocked this fault. And we got earthquakes along here. And then not surprisingly, a little bit later, we got the magnitude 7.1, which slipped these two blocks right laterally or to the northwest relative to the pink block here. And look what that did to the Garlock fault. That kind of unclamped this section of the Garlock fault. Now the Garlock is a really big fault. It's had a lot of motion. It's moved to about 65 kilometers over its lifetime, 40 miles. And it's thought to be capable of a magnitude 8 earthquake, but it's been really quiet in historic times. And so, it's true of any fault, every day we're one day closer to the next earthquake, but there's a lot of concern that the Garlock is overdue for a big earthquake and that this earthquake pair kind of serve to unclamp it and maybe bring the time of the next earthquake there closer. So that's what happened in Ridgecrest in 2019. Let's go back to 1872 and talk about the Lone Pine earthquake. This was a massive earthquake, magnitude estimated at around 7.8. There were no seismometers to measure it with back then. That's estimated based on damage and however the area was felt and so forth. It's roughly the size of the 1906 San Francisco earthquake, but in a much less populated area. So I'm just going to read you what we wrote in Geology Underfoot about this. So we said the earthquake struck at 2:25 a.m. and leveled nearly every adobe, brick, or stone building in the Lone Pine area. 23 of Lone Pine's 250 to 300 residents perished. Camp Independence Army Post was closed after its adobe walls caved in. The quake caused rock avalanches in Yosemite Valley, 110 miles to the northwest. Word of Lone Pine's devastation was slow to reach the outside world. The San Francisco Chronicle noted in its March 26, 1872 edition, the residents of Sacramento, 220 miles northwest of Lone Pine, ran outside in their, quote, frilled nightshirts, unquote. The March 31st edition carried more news and squelched earlier rumors of giant chasms and volcanic eruptions. By the April 7th edition, however, the volcanoes were back again, as reported by the newspaper, quote, 2 volcanoes are reported in active eruption, emitting rocks and flames, roaring like furnaces. Eruptions in great numbers are reported from the Death Valley region, where the earth is reported to have sunk several hundred feet. Well, the earth didn't sink several hundred feet, and there were no actual eruptions during that time, but there was a lot of damage. And you can see the fault that broke right near Lone Pine. This is a chapter in Geology Underfoot. This is just a mile west of Lone Pine. The Whitney Portal Road just goes right up here. These are the Alabama Hills. And in this panorama, this scarp is the scarp that broke in 1872. And it looks curved here. That's because of the wide panorama, but you can go right up to this thing and walk around it. And here it is with my co-author Art Sylvester standing on top. Art's over 6 feet tall, and this scarp jumped up. This side that he's standing on jumped up about 6 feet in 1872, and to the right about 15 feet. So it was mostly right lateral with some vertical movement on it. So obviously the scarp here, which is 20 feet tall, wasn't all built in 1872. It was built over several great earthquakes, but it's really something to see. And you stand there on one side of it and imagine the other side moving, diagonally over and up roughly 20 feet in the matter of a couple of seconds. That's about how long it takes for these faults to break at the surface. It's kind of amazing. Everything on this side where Art is standing, the Alabama Hills, Mount Whitney, Central California, everything else moved at that instant relative to the side that I'm standing on when I took this picture. It's really, I always find it shocking to stand there and try to imagine what that was like. If we look at mapping of faults in the Lone Pine area, here's Lone Pine and Highway 395, and the scarp we were looking at in the last picture is this over here. It's not on the main trend of the Owens Valley Fault, which is several strands that run up Owens Valley here. This is the Mount Whitney Golf Course south of town. This is Diaz Lake, which apparently formed during the 1872 earthquake. So let's go down to the golf course and look at what we see there. So here we're looking west from the tee at hole number 5, which is a 200-yard par 3. And there is the flagstick, and you're hitting, it's kind of a long par 3, and you're hitting uphill onto this 20-foot scarp. So it kind of makes the whole play kind of long. But then the next hole, hole 6, the tee is here, and it's a long par 4, but you're hitting off of that scarp downhill, so you get some extra yardage. So that's a nice interplay between earthquakes and golf, which I never thought there was. If you go north of town, just north of town on the west side, is the common grave for the victims of the 1872 earthquake here. This is 395. You park on the side and you walk up this little hill to the common grave site. And fittingly, this hill is a scarp along the Owens Valley Fault that did the damage. Breakage in 1872 has been mapped from south of Owens Lake down around Olancha in the northern Coso Range, all the way up to north of Big Pine around Klondike Lake. And Klondike Lake is there because of this little branch of the fault. There isn't much vertical offset on the Owens Valley Fault here, but if you get up in the air, it's pretty obvious. There's a small scarp with maybe 1 or 2 meters of offset, but this line of vegetation marks the scarp. And this pond here is a sag pond produced when right lateral slip opened up a fracture that caused a little sag to form. If you imagine putting your hands on either side of the photo and moving them in the direction of the ocean, any fracture in this orientation will be opened up. And without the arrows annotating this, you could take a geologist here, show them this and say, oh yeah, that's a big right lateral fault. You see these things along the San Andreas Fault all the time. So this is just east of Independence. You can just drive out the road east of there and see it quite easily. If we look at mapping of historic fractures in a broader area, all the red fractures on this have happened in historic time. So all of this is from the 1872 earthquake. This stuff up here is from the series of magnitude 6 earthquakes, Mammoth Lakes in 1980. This is the Chalfont 1986 earthquake. So there's a lot of breakage there in historic times, but if we go back to the last breakage in the last 15,000 years, which is since the glaciers receded, we can see a lot more breaks in that time at the base of the mountains here, all over the volcanic tableland and going right through the town of Bishop itself. So it's not surprising to anyone that there are a lot of earthquake ruptures in this area. They're recent and they're ongoing. So I've taken the earthquake catalog and I'm going to show you a little animation of earthquakes since 1820 greater than magnitude 4.5. Now remember, before seismometers were invented, well into the 20th century, the only way people knew there were earthquakes is if they were there, and this was a fairly unpopulated area at that time. And we can only guess at the magnitude. So you're going to see not too many earthquakes early on, and then the number of them go up quite a bit as seismometers get invented and people start occupying this area. That was a big San Andreas earthquake there. There's 1872. We're coming up on 1906, right about now. And And then we start seeing a bunch of them out here in the Mojave Desert and Baja and the Gulf of California. And this is going to end up with the Ridgecrest earthquakes right here. There's some Mojave Desert earthquakes coming up there. And there's the Ridgecrest earthquakes. So that's a lot of earthquakes, and it's kind of hard to make sense out of that pattern. So in the next image, I have taken all the earthquakes greater than magnitude 6, and the ones greater than 7, I've colored a purplish color. I hope you can see that. And these bigger earthquakes make a very clear pattern. They're a nice linear trend coming up the plate boundary in the Gulf of California. And then they fork into a Y, kind of a tuning fork shape with one branch going along the San Andreas Fault. That makes sense. But another big branch with a lot of magnitude 7s coming right up through the Mojave Desert and Owens Valley. And the meaning of this is kind of clear. If you step back and plot those earthquakes, here's the San Andreas Fault making this big bend in the vicinity of Southern California, and Baja's ramming in there, and this stuff's just in the way, and it's basically slowly being captured. And these earthquakes represent breakage along what will probably in the future become a new plate boundary. So we've got, these are all magnitude big 6 or higher. Most of these are magnitude 7, and they line up very nicely along there. And with all the GPS data available now, this is really obvious. So this is from the UNAVCO GPS velocity viewer. You can go there and plot these things up yourself quite easily. What they've done is taken motion over several years for all of these stations. And this is only, I think, 10% of the stations that are out there. Because if you plot them all, it's just too hairy. You can't see anything. And these are motions relative to stable North America. So Colorado Plateau, I kind of think of it as Kansas, just sort of relative to North America. This is how everything is moving. And you can see off on the right side here, there's some tiny little arrows. An arrow this length is 25 millimeters or 1 inch per year. So tiny little arrows over here. They're a little bigger in Nevada. Then when you get over towards Owens Valley, they start to get a lot longer, up to kind of 1/2 inch a year, a centimeter or so per year. And then they get longer and longer over here, but they're all parallel to each other, and it's kind of hard to see what's going on. So what I did was I downloaded all of the station data. And since they're all going northwest, the direction is known. And so I just calculated the length of the vector. So that's the velocity in millimeters per year. And it makes a really nice pattern. So here it is plotted up in 0 to 5, 5 to 10, et cetera, bins and colored. So you can see the Colorado Plateau and most of Nevada and all through Las Vegas is here. This is all the way over to the east side of Death Valley. It's all black, which is less than 5 millimeters a year relative to North America. And then suddenly at Death Valley, on the other side of Death Valley, the Panamints and Inyos and so forth, they're all moving faster, 5 to 10 millimeters a year to the northwest. And just the way this is colored, this is just how it came out. You could draw a boundary right up Death Valley, and that makes perfect geologic sense. But then these purple ones are bounded on the west by the trend I was just talking about, coming up out of the Gulf of California, through the Mojave, right along the trend of all of those big earthquakes and up the Owens Valley. And everything to the west of that is moving faster, 10 to 15 millimeters a year. And then you get over to the San Andreas Fault. I think it's pretty obvious how you would draw the San Andreas Fault through here. And so these GPS velocities are just bearing out what the geology is showing so well, it's almost scary. They agree so well. So I think this is just a beautiful diagram that explains a lot of what we see in Eastern California. Now, one question that comes up with this is, okay, Owens Valley has right lateral motion across it. I was taught in my intro geology class that it was a graben and it was formed by blocks pulling apart in the valley, sinking down, but really most of the motion is right lateral, with the Sierra Nevada moving north and northwest relative to the Whites and Inyo. So how long has that been going on, and how much slip has accumulated? Well, it turns out that about 65 kilometers of slip is accumulated. We know this from studies that my group have done. I first got a hint of this by tracing out the Golden Bear Dike, which is a really giant granite dike that kind of trends east-west, crosses the John Muir Trail north of Forester Pass, comes over the mountain front and down to the mountain front around Independence, points right at the Inyo Range, and there's nothing like it in the Inyo Range. It's not there. Now, nobody says it had to have gone that far, but if you go down into the Coso Range, south of Owens Lake, there's a dike, and it's a series, 2 or 3 dikes of identical age, composition, and everything else that are not present across the valley in the Sierra Nevada. And so when I saw that, and one of my students, Andrew Kylander Clark, worked on that for his master's student thesis, if you line those up, I said, does it violate anything if we line the Golden Bear and Coso dikes back up? And in fact, it makes a lot of things line up a lot better. Golden Bear Dike is unfortunately not all that photogenic, so I'm going to show you a more photogenic feature that lines up. This is the Independence Dike Swarm. This is Mount Prater, which is just north of Split Mountain, beautiful little peak to summit. And these vertical lines, some of them are fractures, but most of these are thin panels of dark gray basaltic or andesitic rock that is intruded fractures there and form a dike swarm. So dikes are just panels of rock that are magma that are intruded and freeze. Independence Dike Swarm is a giant dike swarm that crosses about a 600-kilometer reach of California and is offset across several major faults. So this is where it's densest, up in this area. Really, Woods Lake Basin above Sawmill Pass is kind of the best exposures of that. I'll show a picture from there in a second. And so this dike swarm is really intense in the Sierra Nevada and on the eastern range front. And if you go up and stand in this notch right here and look to the southeast along the trend of the dikes, you're seeing this. So this is John Bartley, who worked with me on all of this work, and he's looking southeast. This is Mount Tinnemaha. You can see this black stripe here. This is a 10-meter wide dike. There are several other giant dikes here. There are hundreds of dikes cutting through Tinnemaha and the cirque that contains Red Lake below Split Mountain here. And they all point right at the Inyo Range, and there aren't any over there. We've done surveys all over the White-Inyos in Sierra Nevada to quantify this, and there just aren't any over there. If you want to find them again on the other side of Owens Valley, you have to go down to Ridgecrest. The Coso Range, Spangler Hill south of Ridgecrest, the Argus Range. This is a air photo of the area just west of Cyril's Lake. This is the little town, or the little hamlet of West End here. And these are the dikes and down in the desert there. So we got to do a lot of really fun field work backpacking in here and measuring and counting dikes and all. This is the Golden Bear Dike, this pink thing here that comes down to the mountain front around Independence and then reappears down in the Coso Range. And the size of these circles represents how inflated the crust is by dikes. And Woods Lake is where they're the most. They're about 50% of the crust there in this amazing exposure here. If you go across the valley, most of these dots are zeros, actually. They're not a few dikes, they're zeros. There are just a few places where you can see them, including on the northeast side of Owens Lake right here, these beautiful pair of dikes cutting marble. These played a cameo role in the epic film Tremors. When the farmer is out raking and then bad things happen to them, the dikes are prominent in the back of that. So that's a good excuse to go watch Tremors again if you haven't seen it in a while. And the dikes down in Ridgecrest area are quite dense, but they're not real photogenic except for this guy, which we call the Stegosaurus dike, which is right where Highway 178 makes the turn to the north to go up to Trona. And the offset between the dense dike swarm up here and the dense dike swarm down here, it's a little harder to estimate than the Golden Bear, but it's maybe 75 kilometers, but it's roughly consistent with it. And there are two other features that line up when you restore the Golden Bear as well. So we're pretty confident in somewhere around 65 kilometers of right lateral slip across Owens Valley here. So when did that happen? Well, The Golden Bear Dike is the youngest thing we know of that's cut, and it's 83 million years old. So it's happened in the last 83 million years. Is that mostly loaded toward our time, or has it been very gradual? We don't know. Maybe there's some ways to find out, but we haven't gotten there yet. I want to talk about one other thing related to this that has to do with the Kern Canyon fault. So this is Kern Canyon Gorge here. If you know the Mount Whitney area, you're very familiar with this, and it's along a right lateral strike slip fault, most of which was active some time ago. But in doing the work for counting the dikes and all up here, my colleague John Bartley figured this out. We noticed that in this area around Shepherd Pass and so forth, all of the passes through the high country, the headwaters of the Kern, are faults. And the type example of this is Forester Pass. So the John Muir Trail going across the drainage from the Kings River drainage into the Kern River drainage. There's Kern Canyon down there. And Forester is just a notch cut in this big arête. And Junction Pass is the same, just off to the left in this picture. And this is a picture looking the other way, looking north. There's me standing at the top, and all of these fractures going through here and all this reddish staining indicate faults. And these are fault surfaces that are polished by fault movement. They have green epidote on them and slicken sides, which are scratches from one side scratching the other. And every pass in this area, Forester, Shepherd, Junction, Lucy's Foot, Millie's Foot, unnamed passes on the sides of Caltech Peak and all that are faults. And we speculate that maybe these are faults that link up slip in Kern Canyon with slip in Owens Valley, but that's just speculation. I'm not sure how we can really nail that down. So we've started with a picture from the space station. Let's go back to the space station and run up the Gulf of California. There's Baja. So we're going up the plate margin where the plates are spreading apart and forming a new ocean basin up here. And when we get up onto land here and around the San Andreas Fault, that's where the San Andreas Fault starts up. I'm going to pause it here. So the San Andreas runs here in the proper direction, and then it makes this big bend to get through the LA area and then takes off in the proper direction again up here. And that's the cause of all the trouble that I've talked about. And all those big earthquakes were on a line just running right up here. Here are the snow-capped Sierra. So I will stop it here. And here's White Mountain Peak and the Inyos and so on. So that new plate boundary seems to be forming right up here. And all of these big historic earthquakes are a manifestation of that movement of the plate boundary inland. So you can see that pretty well from this height. It'd be nice to go up there sometime and see it myself, but it's just because of this misfit in Southern California that we're ramming this new plate boundary through up there. So that's my story. I'm sticking to it. The story belongs to a lot of people. I don't want to just take credit for it myself, but I will say that if you have any questions, since I can't answer them in person on this recording, feel free to email me. My email address is here, and I would love to talk to you about it. Thank you very much.